Hello and welcome again to A Minute with a Molecule. Today we have this molecule here which I will not name. I just want you to stop for 1 minute. Take a look at this molecule. Of course, assuming that you are an IB Chemistry HL student, think about all of the connections you can make to what you studied in your IB Chemistry course. Of course, this series is made really with students who are reviewing the course in mind. And if you are reviewing the course and you are an HL student, I want you to think about all the connections you can make between this molecule and what you learned in IB Chemistry. Of course, if you're an SL student, you can do the same, but the expectation would be a little bit less. So once your minute is up, I will share with you an exemplar answer. So let's take a look now at the exemplar answer, and let's start by naming the molecule. And this molecule is named 2-bromo-2-methyl-propane. And you have to think about it like this. The longest straight carbon chain or continuous carbon chain is 1, 2, 3. That gives the molecule the suffix propane at the end. And bromo is on carbon atom number 2. No matter which direction you go, it's going to be 2-bromo and 2-methyl, 1, 2, 3, making it propane, and this making it a methyl group on carbon atom number 2. So 2-bromo, 2-methyl-propane is the correct IUPAC name for this molecule C4H9 Br. It's a halogenoalkane, and this is its molecular formula right here, and here you have its structural formula. Of course, seeking to make as many connections to the IB Chemistry guide as possible, let's talk about the hybridization of each of these carbon atoms. 4 bonds involved, 4 domains, meaning sp3 hybridization. Here we have a very polar bond between carbon and the bromine, this arrow indicating that the pair of electrons in this covalent bond are held a bit closer to the bromine, which is much more electronegative than the carbon, giving a small negative charge, delta minus, and a small positive charge, delta positive, and a polar bond. A polar bond just in this one spot, of course, means that we would have a polar molecule with a dipole shifted towards the bromine side. Now, let's focus a little bit on some organic chemistry. This molecule, when reacted with sodium hydroxide, undergoes an SN1 reaction, a substitution reaction, with a nucleophile that has a rate-determining step that is dictated by a single molecular entity, the halogenoalkane. So let's consider us having this reaction here with sodium hydroxide. What you actually have is a tertiary halogenoalkane, meaning to say that the carbon atom that holds the halogen atom, that in turn is attached to 3 other carbon atoms, making this a tertiary halogenoalkane. Tertiary halogenoalkanes would mean that if this tertiary halogenoalkane is reacting with sodium hydroxide in solution, the hydroxide ion has a lone pair that it can donate to this small positive charge here on the carbon. And it will be attracted to that positive center, making it a nucleophile, literally meaning something that is in search of a positive center. Nucleophiles, of course, are also Lewis bases. They can donate their lone pair. This nucleophile also happens to be a Bronsted-Lowry base. It can accept a hydrogen ion. So nucleophile can be all of those things, but this hydroxide ion is drawn towards the small positive charge. But before that happens, bromine exits, and you have what is formed here is a carbocation, a positive species with a full positive charge that is stabilized by the inductive effect. And following Markovnikov's rule, the stability of this will be very high because it's got 3 alkyl groups attached to it, which would have a tendency to donate electrons. And this is the rate-determining step in this reaction, this exiting of the bromine and the formation of the carbocation. And then the hydroxide group enters into the space where the bromine has left. So there would not be any what we would call inversion of configuration here. The Walden inversion would not be a part of this SN1 reaction. But the solvents that we use would have to be a polar solvent because we are dealing with charges and we need a polar solvent to support that. But we also need a protic solvent, one like water or ethanol, which would surround the hydroxide ion and allow for the formation of the carbocation. And then once the carbocation is formed, it would pull the hydroxide ion away from its shell and allow the last part of the reaction to happen. So the rate determining step really is just where the halogenoalkane forms the carbocation. And that's why this reaction is said to be unimolecular. The rate is controlled by a single molecular entity, and the rate equation or the rate law for it is K multiplied by the concentration of the halogenoalkane, making this an SN1 reaction. And this would be the product here, with the OH coming into the very spot where you had the Br. Now, the sp3 hybridization that I mentioned earlier here also lends itself to a tetrahedral electron domain geometry and molecular domain geometry. Finally, not forgetting spectroscopy. And this molecule C4H9 Br has 9 hydrogens in a chemically equivalent environment. The chemical shift would not be that much because they're CH3s, not too much de-shielding. So they're just going to be at sigma 1.7, a little bit down from where tetramethylsilane, the standard molecule, is in NMR spectroscopy. But you'll have a peak that corresponds to 9 equivalent hydrogens. Its mass spectral data would, of course, correspond to its full molecular formula of 137. One other important peak that you will get would be at 57 for the C4H9 positive strand. Of course, remembering that all mass spectral fragments are given a positive sign. And quite possibly there are more connections that you can make between this molecule and the IB chemistry guide, but having made this number of connections, the student would demonstrate a very comprehensive understanding and great preparation for the final exam. And if you can make all of these connections that I just made, you are most likely in line for a 7 in the examination.